Hello, I'm Jim Jeffers. I lead Intel's advanced rendering and visualization team that develops the Intel oneAPI Rendering Toolkit. In this video, we show our collaborative work with Argonne National Labs for the HACC simulation and analysis framework computation dubbed The Last Journey. The Last Journey is a large volume gravity-only cosmological n-body simulation involving more than 124 trillion particles. The cosmological parameters are chosen to be consistent with the results from the Planck satellite. The simulation allows us to follow the evolution of structure formation over cosmic time and study the impact. The simulation will be important to aid for the preparation of data arrival from future cosmological surveys. Some things to keep in mind as you view the visualization. Using particle volume rendering in Intel OpenVKL, we show particles that signify tracers of dark matter which coalesce over time into clumps or halos where galaxies then form. We have a color-mapped velocity magnitude. Turquoise, yellow, and red regions correspond to faster-moving galaxies. We use Intel's Osprey Studio framework as a front end for post-hoc visualization. This allows us to load the time series, manipulate transfer functions, and specify rendering parameters. Now for a few interesting statistics and some info on the visualization techniques. This video shows just a subset of the Last Journey HACC simulation consisting of roughly 12 million particles out of the 1.2 trillion particles simulated across the time steps. As it evolves over the full time series for this tiny portion, over 225 gigabytes of data is in memory. You don't have to be a rocket scientist to do the upscaling math from millions of particles to trillions to realize the processing and data footprint for running the full simulation is of exa magnitude. The simulation begins as a homogeneous distribution of dark matter as it was shortly after the Big Bang. Galaxy clusters start to coalesce and still at high velocity. Dark matter filaments form and velocity decreases. The filaments disperse and velocity decreases even further. In Osprey Studio, we can manually move the timer to inspect individual time steps. Here we zoom into a galaxy cluster. We can change the transfer function and opacity scale to adjust the look and exposure of the volume rendering. We can switch from breakcasting to path tracing. While slower, path tracing allows for better depth cues. Progressive rendering in Osprey Studio maintains interactivity and helps in developing a look for high-quality batch visualizations or in-situ visualization. Osprey Studio lets us save scene state, which can be subsequently used in offline or in-situ production. We can even add lights to further refine the visualization. I hope you enjoyed this brief look at HACC cosmology simulation and visualization. As the Aurora exascale machine comes online, We hope to update you on the new discoveries the team makes about our universe. Have a great day.